Hi, this is Lauren Mitros. Today I will be solving heat transfer problem 1.57 from the 8th edition of Fundamentals of Heat and Mass Transfer by Bergman and Levine. So problem 1.57 states that the wall of an oven used to cure plastic parts is of thickness L equals 0.05 meters and is exposed to large surroundings and air on its outer surface. The air and the surroundings are at 300 Kelvin. If the temperature of the outer surface is 400 Kelvin, and its convection coefficient and emissivity are equal to H equals 20 watts per square meter Kelvin and epsilon equals 0.8 respectively, what is the temperature of the inner surface of the wall if the wall has a thermal conductivity of K equals 0.7 watts per meter Kelvin? So our first step is going to be writing down our givens. The wall thickness is 0.05 meters. The temperature of the air and the surroundings are equal at 300 Kelvin. The outer surface of the oven is 400 Kelvin. The convection coefficient is 20 watts per square meter Kelvin. The emissivity is 0.8. And finally, the thermal conductivity is 0.7 watts per meter Kelvin. We need to find the temperature of the inside surface of the wall. So we can start by drawing our diagram. We'll start by drawing a cross-section of the wall, which we can then label our inner and outer surfaces. We need to denote our surrounding surfaces and the surrounding air. Now we can add our coordinate system in X and the thickness of the wall. Since the wall is solid, we know that we will have conduction through it. My sign convention is from the inside to the outside. Now we can add heat flux due to radiation and convection. Next are our assumptions. We can assume that the system is operating at a steady state. Energy is conserved. Small object, large enclosure. No generated or stored heat. Closed system, so no mass transfer. Constant isotropic properties. And one-dimensional conduction in X. Now we can write down our general equations. First is the energy balance equation. Energy stored is equal to the energy in minus the energy out plus the energy generated in our boundary. In our assumptions, we assume that no energy was stored or generated within the system, so these two terms can equal 0. We can rewrite the equation as the energy in is equal to the energy out. Next are heat flux equations for conduction, convection, and radiation. Finally, we can start to solve the problem. So I'm going to redraw the outer boundary of the oven. We know that there is conduction through the wall and convection and radiation on the surface. This is because our energy balance. Energy in must be equal to the energy out. So therefore, the heat flux of conduction is equal to the sum of the heat flux of convection and radiation. So first up, we're going to solve for convection. After plugging in the terms and canceling out units, you can see that the heat flux of convection is equal to 2,000 watts per square meter. Next, we'll solve for radiation. Once again, plugging in our terms and constants and canceling out units, you can see that the heat flux of radiation is equal to 1,213.8 watts per square meter. Since convection is equal to the sum of convection and radiation, we can plug these two terms in and find that the heat flux of conduction is equal to 3,123.8 watts per square meter. But we aren't done yet. We still need to find the temperature of the inner surface of the oven. So we will set this term equal to the equation for the heat flux of conduction. We can then rearrange that to solve for the inner temperature, plug in our variables, and find that the internal temperature is equal to 2,695 degrees Kelvin.